Hi there, so we've reached our final probability lesson, which is going to be about one of my favourites, tree diagrams. And what's brilliant about tree diagrams is so many ways of looking at probability are great, but they're only great if you're looking at one or two events. Once you get to more than two events, tree diagrams are superb because you can just keep on going. It gets more complicated, but you can just add another layer on another layer on another layer with each event that goes by. So let's have a look at those. Here's our first example. So pause the video and give it a go. You've probably done tree diagrams before anyway. Right, so when we start with our first sock, that's going to be done by one of two lines. So you could have a black sock and you could have a pink sock. And we've got 11 socks altogether. So you've got a 7/11th chance of getting a black one and a 4/11ths of a pink. Then because it's non-replacement, we're going to be wearing these socks after all. Pair of pink socks, lovely. But we're looking for black. So black and then black. Because we've already taken one black, there's only 6 left. And there are only 10 socks left in the drawer. So that's got a bit less likely. The pink have got a bit more likely because there's still 4, but there's only 10 altogether. And then black and pink, if a pink has already come out, then there will only be 3 pinks left out of 10. If a pink has already come out, there will still be 7 black socks out of 10. And then with a tree diagram, because and means multiply and or means add, we multiply along the branches. So for both socks are black, it's going to be 7/11ths multiplied by 6/10ths, which is 42 over 110. And if you like, you can simplify that to 21/55ths. Although, to be honest, I like keeping it over the original one because all of these things are going to add up to 110 when we do them all together. If we do this now, 7 times 4 gives us 28 over 110. 4 times 7 also gives us 28 over 110. And 4 times 3 gives us 12 over 110. So if you add up 42, 28, 28 and 12, you get 110. Whereas it gets a bit confused because if you've got different numbers over, sometimes they simplify to different denominators. So our black socks, both being black, is 21 out of 55. The socks are not a matching pair. Well, we've got 2 routes that can do that. Black and then pink, or pink and then black. They're both the same, but they're both 28 new ways that it could happen. So it is an or situation for that. And or in probability means as it works with this one or that one, it makes it more likely. So you add your probabilities together, and you don't need to worry that it's going to go over 1, because if we were to add everything that can happen together, it gets to 110 out of 110. So that gives us 56 over 110, which we could do down to 28 over 55 if we wanted to. Okay. Right, so here's your first of 3 questions I'm going to give you to have a go at. So obviously pause the video, have a go at all of this, and then compare it to what I've done. So you should have a tree diagram that looks something like this. If he shoots a par, then he's going to be really happy, isn't he? So it is affecting how well he does. He then does even better he's got a better chance of doing well on the next hole. So par is good in golf, under is even better than that, over is not so good. So if he gets off to a bad start, the chance of him doing badly on the next hole are increased because his swing's not that great that day, or maybe he's just feeling a bit under the weather, or maybe this has happened because the weather's bad, or for whatever reason. All of this comes up to say with the second part when it says state whether or not they're independent. They're not independent. If they were independent, how he did on one hole would not affect how well he does on the next hole, which it clearly has. Right, find the probability that Mr. Dixon scores par or under on only one hole. So this is 2 holes. This is no holes. So we are interested in that one and that one. So this one is going to be 0.7 multiplied by 0.2, giving me 0.14 for par and then not. But then if he doesn't do it the first time, it's going to be less likely does it the second time. 3 4s are 12, so it's just that the second time. So then, because it's or, we add those two together, giving us 0.26 as our final answer. Here's the next question about flipping a coin 3 times. So give this one a go. So this is what your tree diagram should look like, something like. Gets a little bit tricky, so here's the third flip of the coin, doubles up the number of branches. The probability all 3 coins lands on heads each time is going to be a third times a third times a third, which is going to be 1 over 3 cubed is 27. Find the probability that the coin lands on heads only once is going to be trickier, because we have got more ways that this can happen. It can be a head the first time, but then not and not, so it could be that one. It could be a tail and then a head and then a tail, or it could be tail, tail and then head. So we've got 3 ways. Each way is going to be the same probability as itself, because you've got a third times 2 thirds, whereas on this one it'll be 2 thirds times 1 third times 2 thirds, and I just realised I said something different because I've made a mistake, haven't I? That's not a third there, that's 2 thirds there. So it's 1 times 2 gives us 4 over 27 for each of those. And this last one is going to be 2 times 2 times 1, giving us 4 over 27 again. So you've got all 3 of those coming in together, giving us 12 out of 27. The whole experiment is repeated again. Find the probability of obtaining either 3 heads or 3 tails in both trials. Okay, so this is going to take a little bit of thinking. First of all, we've got to think about either 3 heads or 3 tails in one of the trials, which is what we've got here. So we've got 1 over 27 there. Oh, incidentally, that could be simplified, can't it, to 3 goes into that bit, 4/9 you might have had there. Then if we come down here, we've got 2 times 2 times 2, which is 8 over 27. So either 3 heads or 3 tails in one trial equals 1 plus 8 over 27 is 9 over 27, which is a 1/3 chance. So the probability of 3 of a kind basically is a 1 in happening in one of the trials is a 1 in 3. Of it not happening is a 2 in 3. And so if we do that again, we just need to worry about that. We want to get 3 heads or 3 tails in both trials. So it's a 1/3 times 1/3, which is 1 over 9. You might want to rewind that and think that through again. Right, so here's today's final question. Pause the video, take your time, especially on the last part, because it gets a little tricky. So the setup for the 2 should look something like this, which does give you 30 over, what is it, 156, isn't it? Which does come to 5 over 26. Now the first part, it's only 1 mark, and that's because they're saying what's the probability the third token is yellow given that the first 2 are yellow. So if the first 2 are already yellow, it's just saying what have we got left now, and you've got 4 yellow ones left out of 11 tokens altogether. Now the last part you'll notice has got more marks than the other two put together, and that's because we want the probability all three tokens are different colours. Now you can get in a right old muddle because of the number of branches going on, so let's not worry about drawing the branches we don't want. If you've already got two blues, then it's out, isn't it? They've all got to be different. So it's got to be blue, red and yellow. It's then also got to be blue, yellow and red. So let's think about what they would be at that time. At that point we've still got 6 yellows left out of 11. At this point we've still got all 3 reds left out of 11. When they're all different, they're all going to have their original amounts left, aren't they? So red, blue and then yellow would be 6 left out of 11. That makes it simpler to think about. 2 reds, that's already gone. Already gone. Red and yellow, it's just the blue. And that's 4 out of 11. Yellow and blue, just the red. That's 3, isn't it? Yellow and red, it's just the blue. And because we can't have the yellows, we can ignore that one down there. Sorry, what was the blue? It was 4 out of 11. Then we just need to do multiply, multiply, multiply for each one of these and then add them up at the end. That should look something like... So that, first of all, I'm getting 6 out of 143, but I'd just like to pause at that point because my calculator automatically simplified it, which I would find annoying, except of course that if you look at these numbers, they're all the same numbers every time, aren't they? They're just switching over. So that's going to be a 6 out of 143. This is also going to be a 6 out of 143. And in fact, as I go down, I start to think, do I even need to do all of that? Do I just need to count how many I've got? I've got 1, 2, 3, 4, 5, 6 roots that all actually have the same numbers. So I'm actually getting 6 lots of 143. Or it's a 6 times the... So what I'm going to do there is just multiply the top number, aren't I? And that's going to give me 36 out of 143 as my final answer. So you may well have got there differently. And if you haven't got that answer, then go back again and just listen to me go through that one last time. Anyway, that's it for probability for now, folks. That's been fun, I hope. And see you next time. Cheerio.